Hi, everyone. This is Dr. Jeff Stratford from Wilkes University, and welcome to Biostatistics and Experimental Design. This chapter, chapter 5 in the text, is exploratory data analysis. This part 1 is going to cover measures of central tendency, which is where most of your data lies. All right, that's what it means. So when we go over this chapter, I want to get familiar with understanding what descriptors are doing. So this one, central tendency, just means, and I'll give you the example. So like average, median, mode, it just means where most of your data lies along a line, okay? So is it towards 0? Is it far from 0? Let me put out one thing, why we call this exploratory data analysis and not just descriptive statistics like many chapters and other books do. I call it exploratory data analysis because whenever you are given a set of data, whether you collected it yourself or somebody else collected it and it's your job to analyze it, what you want to do is you should always understand the experiment that led to the data, but then you should start working with the numbers to be intimate with the numbers. And what I mean by that is know where the problems are, if there's outliers, and just be able to visualize in your head what some of these numbers mean. And my commandment, my statistical commandment is know thy data, okay? And like I said, what that means is if I told you, if you studied, say, the size of trees in a forest, okay, you should have a pretty good understanding of what, say, 35 centimeters diameter breast height, what that means. If you're given health data, you should know what are reasonable numbers for something like heart rate. So is a heart rate of 35 normal? Is a heart rate of 72 normal? Is a heart rate of 120 normal? Right? So understand your data. All right, let's get started with the lecture. All right. All right, so the first thing let's go over is you should already know this, the arithmetic mean. Okay. If we're talking about a hypothetical distribution, then the symbol we use is mu, okay? And we can say that equals x bar. Okay, that's the mean. And what we want to do is sum up our observations and divide by the number of observations. And that's it. Okay, so hopefully you've seen this calculation many times, and hopefully you've actually done it many times before. All right, next, weighted means. A weighted means, okay, so you have some observations, okay? And let's say you take some measurements and you have 4, 5, 7, 9, 2, and 5. And let's say that you want to, so these are your, we'll say xi's, okay? And you think that for whatever reason, this observation deserves more weight. Okay. Weights do this. They can either increase an observation's importance or decrease. And so if you want to increase this observation, so let's say this is some measure of a country's impact, right? Their score, but let's say the population here is 3 times that of the rest. What you can do is say, sorry, oops. If we wanted to make this observation worth 3 more, we just multiply it times 3, okay? And then we add everything up, okay? And then what you do is you divide by the weights, okay? If you don't articulate a particular weight, then just assume it's 1, okay? So in other words, if you're doing a weighted mean, it's actually 4 times 1 plus 5 times 3 plus 7 times 1 plus 9 times 1 plus 2 times 1 plus 5 times 1. I like using parentheses because it removes ambiguity, okay? And then you divide by, don't know why my pen is doing that, divide by the weights, okay? So in this case, it would be 1 by the sum of the weights, 1, 4, 5, 6, 7, 8 by 8, okay? So this may seem weird, but actually the mean, just a regular arithmetic mean, is doing the same thing, right? But it's just that every observation. So you would have 4 plus 5, right? 4 times 1 plus 5 times 1. When you add these up, it's going to be the same number as n, right? So the weighted mean is just accounting for the weights, okay? And even though these things are, you think they're unweighted, but the weights are actually 1s. So you just add that all up, and there you go. There's your sum, right? So let's say the population for that country was 3 times as large as the rest. You could actually do something like multiply it times a fraction, and it would make this less important, right? This observation less important, okay? So that's how weights are used. It's a way that you can unlevel the playing field because you have some reason that you think some observations are different from other ones. An example I give in the book is that you look at a number of activities that affect health. And let's say you score all those activities on a scale of 1 to 5. And it could be something like how many cookies you eat, right? You scale 1 to 5, where a middle number would be the average and 5 would be, much more than average, and 1 would be much less than average. And it could be things like activity level, but let's say you include smoking, where 1 is a non-smoker, and then 5 might be like something crazy, like 3 packs a day. And since we know smoking is that harmful, you may weight smoking, so everything is measured on the same scale, but you may think that smoking has more of an impact, so you'll weight that variable more, right? So when you get an average of, say, health indices, that smoking's weighted more, okay? Or if you don't think cookies are important, then you can make that a fraction. How can you hate on cookies? All right. The median. All right, the median is, give you a definition. When observations are ordered, the median is the middle number. Okay. And what I mean by ordered is, let's say our observations are 3, 5, 7, 2, 9, 1. It's 1, 2, 3, 5, 7, 9. And so the median would be the middle number, right? So if there was a 4, it'd be 4 here. What you do is, if you have an even number of observations, you can take these two and get the average of these two, and that'll give you the median, okay? But if you have an odd number, like say there was an actual 4 in here, it would be 4, okay? Because it's the middle number. So you have as many numbers on this side as you do this side, okay? And that's the median. When do you use the median as opposed to the average? It depends on the shape of your data, okay, and what you're trying to get across. So often the average is used when the data are more or less normally distributed, okay? When data are normally distributed, okay? So here's the frequency, and here's values of X. And normal might look like this, okay? If that's the case, let's see if I can get rid of that. Okay. If this is your curve, then the average will be right there, right? You could say X bar, and this also is where the median, okay? Median's often used when the data are highly skewed, okay? And so it isn't the middle number. So this is what I would consider to be a misconception. In fact, it's hard to get through my own head. The median isn't, if you look at these numbers, you just pick the number right in between, right? So you would take the smallest number, largest number, and whatever's in between, that's the number you have. That's not what this is, right? What you have is a large number here, because remember, you want as many observations smaller as you do larger, okay? So when there's a long tail, the median might be somewhere in here, okay? And the average will be here. These things are pulled away, right, by this skewedness, okay? So these observations are pulling the mean and the medians away from the peak, okay? All right. The mode. So the mode is the most frequently occurring number, okay? So the mode is the most frequently observed value. Okay. So here's another thing. You're often told that modes are used for counts, and counts are very appropriate for the mode. Okay, so for example, if you look at the number of eggs in a clutch of, I'll say, bluebirds in Pennsylvania, you'll have a few where there's only 2, some where there's 3, a whole bunch have 4, 5 is probably the most, 6, 7, and maybe even find a few with 8 out there. So this would be the mode, okay? So when there are counts, it's very straightforward, okay? So obviously when you have counts, modes make sense. However, let's think about continuous numbers, okay? And first, let me give you a bunch of counts. So like 3, 4. So here's your right. So here's your bird nest data. You would say the mode, right, is 5 because there are 4 of those. There's 2 6s, 2 4s, and only 1 2. Right. Now let's say that these numbers are actually come from a continuous distribution. So let's say this is mass of kidney mass and transplants for whatever reason, right? And these are in kilograms. So if you measure them, we're going to get something like 3.1, 4.7, 5.2, 5.1, 5.3, 6.1, 3.7, 2.9, 5.3, 4.7. Okay, so now you say, what's the mode in here? Now it's actually 4.7. Okay. It's no longer 5 because remember, it's the most frequently occurring value. And even though these have 5, right, in the first digit place, the 10th digit, right, the 10th of a kilogram, none of them are the same. So in this case, the mode would be kind of misleading, okay? And in fact, if you weighed these kidneys on a better scale, you may find that you have 5.71 and 5.72, in which case there is no mode. Every observation is different. So then how do you come up with things like, if you do a histogram of continuous numbers, you will get a histogram that looks like this. Okay, so where does this come from? Okay, it comes from the fact that we're doing something called binning. Ooh, that looks terrible. All right, let's try that again. B-I-N-N-I-N-G, binning. So binning is when you start putting observations together. So you might say greater than 3.0 to 3.5 is going to be a bin. So any observation will go in there. Okay. So binning just means there's buckets and you put even continuous numbers, right? So if you have masses, you could probably weigh every kidney in the world, right? And if you had just the best measurements, you would find that very few of them actually weigh exactly the same. All right. But binning allows you to sort of clump these things together. Okay. All right. I believe that's it. So that is the lecture for talking about central tendency and knowing where your blob of data is. And that's how you start to get to know your data. Next stop will be understanding variation in your data. Or what I like to think of as the shape of your data. All right, see you soon.